Hi, my name is Tom Heffel. This channel is all about helping students learn chemistry. In this lesson, we're going to be talking about the solution process. Now, the solution process deals with intermolecular forces. So we're talking about the breaking up and the formation of intermolecular forces when we're talking about the solution process. And there's 3 steps. The first part is going to be separating the solute particles. Okay, that's going to require energy. So just like bonds, when you break bonds, it requires energy. Okay, and when you form bonds, energy is released. The same thing is true about intermolecular forces. As we break intermolecular forces, that requires us to put in energy. But if we form intermolecular forces, energy is going to be returned. So in the 3-step process, the first step is the separation of the solute particles. That's going to cost us energy. Okay, so that's going to be a positive sign when it comes to enthalpy. And what we're going to be doing is we're going to be drawing some enthalpy diagrams. We're going to separate the solvent particles. Once again, the separation is going to cost us energy. So that's an endothermic process as well. Okay. However, we do get a return on this investment. We get a return based on the formation of solute to solvent intermolecular forces. And that's going to be an exothermic process, and that's going to return some, if not all, of the energy that we put in. Okay, so the first example that we're going to take a look at is putting sodium hydroxide in water. Okay, so we're going to start down here with just sodium hydroxide and water. Okay, now sodium hydroxide is an ionic compound. Okay, and just like any ionic compound, it's going to form some type of lattice. Okay, so this ion is attracted to this ion is attracted to this ion, and so forth. Okay, so it's a very complex kind of system here, and so we got to break up all of these forces. Okay, well, if you know anything about ion-ion intermolecular forces, or I should say interactions, please watch the video previous to this one because it explains all of it. But it's going to cost us a tremendous amount of energy. Okay, remember, separating the solute, okay, is going to cost us energy because we're breaking these interactions. And these interactions are really strong. So I'm going to make my delta H1, which is the separation of the sodium ion with the hydroxide ion, as being very endothermic. Like, I'm going to use we'll use 4 or 5 plus signs here to show how large this is. And we're going to label this as an ion-ion separation because we are separating the sodium ions from the hydroxide ions. Okay, and that's going to be step 1 of the solution process. Step 2 is to separate the water molecules because the water is the solvent. Okay, now water kind of looks like this. Okay, and they're attracted to each other as well. And what we're trying to do is separate those attractions of those water molecules. So that's going to cost us some energy as well. So I'm going to lift this up a little bit more. Now, I don't know if it's as much as ion-ion, okay, because the delta H here, we'll call it delta H2, separation of the solvent molecules. I'm going to give it, a couple plus signs here, okay, like maybe 3 or 4, okay. The separation that's involved in separating water molecules is not ion-ion, okay, but water molecules are attracted with hydrogen bonding. So we're not separating the hardest one, ion-ion, but we are separating one that is fairly high. It's kind of like in the middle, and that's going to be hydrogen bonding. So I'm going to label that as hydrogen bonding. Remember, hydrogen, there we go. Remember, hydrogen bonding is not a bond. It's an interaction that occurs between water molecules, okay? So that's going to cost us energy, okay? So this is a tremendous amount of energy. Separating ions, separating hydrogen bonding, that costs us a lot of energy. Well, what's the return? The return is going to be the formation of solute to solvent intermolecular forces. And what we're creating here is an intermolecular force, between the solute and the solvent. So if this is a positive ion, probably line up more like this as a negative side of the water molecule. And we're going to create this ion to dipole interaction here. And that's going to return us a decent amount. Now for sodium hydroxide, it's going to return us more than what we put in, okay? Because when I stick sodium hydroxide, like if I had a coffee cup calorimeter here and I stuck some sodium hydroxide in here, when it dissolves, it's going to release heat and this solution is going to heat up. So I know it's exothermic because I've performed this experiment already. So I know my return is going to be greater than my investment. But I kind of want to wonder why, because when I think of the interactions that are being formed with delta H3 between the solute and solvent particles, it ends up being ion to dipole. And if you know your list of types of intermolecular forces from the previous video, ion-ion is the highest. Okay, so you'd think, why isn't this magnitude larger than the second most important one, which is ion dipole? Here, ion dipole seems like it's larger than ion-ion. And here's the reason why. Okay, when we come in here and we split up the ion-ion interactions between this sodium ion and these hydroxide ions, it's just not one interaction for each one that I bond that I break up. What happens is you have all of these waters coming in, okay? It could be 5, 6, 7 of them. So you get not like a larger magnitude per one, okay? But because we have 7 or 8, however many water molecules are coming around both the sodium ions, okay, and the chloride ions, you get all these other interactions that are taking place. It's the quantity of them. So think of it as, hey, this might be like a $10 bill, okay? It's worth more than this $5 bill. But if I have multiple $5 bills, it's going to trump the one $10 bill that I have. And that's what's kind of going on in this solution process. So the negative here is going to be great because of the amount of water molecules that are surrounding each and individual ion in the lattice structure. Okay, so our investment might be like $100 and I'm getting $120 back. Heck yeah, this is going to take place and it's going to dissolve. Okay, so if we look right here, we're going to have something that ends up being exothermic, okay, when I get more return than my investment. Now, this doesn't always happen, okay? For example, if I come here and I substitute out the sodium hydroxide for ammonium chloride, well, I've done this in the lab as well. And when I stick ammonium chloride, it's an ionic compound as well, okay? But when I stick it in water, it gets cold, okay? Because the energy is going towards the ammonium chloride, okay? So it's an endothermic process. Well, how does that happen, okay? Well, we still have the same delta H1 because ammonium chloride is ionic, so it still costs us maybe the same amount of energy to split it all up, okay? We're still separating the water molecules, so that's costing us the same. So this piece is about the same, this piece is exactly the same, okay? But what we find out that is with ammonium chloride, okay, the return on the investment ends up falling a little short with the delta H3. Now, it's still ion dipole interactions, okay, but the strength of the ion with the dipole is not as strong, okay, with ammonium chloride as it was with the sodium hydroxide. And what ends up happening is I have a positive overall delta H. And you might say, well, why would anybody do this? Okay, why would somebody invest $100 and only get $80 or $90 in return? That doesn't seem like it's a very good investment, okay? So why would a chemical reaction like that take place, okay? Well, the answer lies with our thermodynamics that we had in the last unit. So I just want to come back and review delta G, which is Gibbs free energy, okay? And Gibbs free energy tells us that a chemical reaction will take place as long as this guy is negative. If it's negative, the reaction will take place, okay? I know this takes place because I've done the experiment, but I just want to show you where it kind of proves that it takes place using Gibbs free energy. So Gibbs free energy is equal to delta H minus T delta S, okay? So in this case with the ammonium chloride, okay, we get a positive delta H, okay? Well, if it was based on enthalpy and enthalpy alone, that would make delta G positive. And remember, in order for it to occur, it has to be negative. So having something that's endothermic does not help this reaction take place. In fact, it hurts it, okay? Now, there's another term though, okay, and that's going to be T delta S. And what delta S is entropy, which is a measure of disorder, okay? And when something that's ionic dissolves in water, we're breaking all this, look at how complex this is. Look how ordered it is, okay? And when we dissolve it, we're just separating all this stuff and we're making it super chaotic, okay? And that's going to increase the delta S or the entropy value, okay? So what you get is a positive minus a larger positive sign. So like if this is 50 and I subtract something that's a larger positive, like 100, well, 50 minus 100 would give you like a number like negative 150. As long as this number is negative, this is going to take place, okay? So as long as this enthalpy is relatively small relative to the entropy change, okay, these reactions will take place. So it's kind of like this. If I was to give you an analogy, okay, hey, invest $100 with me, okay, I'm only going to give you $80 or $90 back. You may say, hey, I'm not going to do that, okay, but, okay, I'm going to let you use my Lamborghini for the day, okay. You say, oh, well, that might be worth it, okay. That's what's going on with Gibbs free energy, okay. As far as the enthalpy change, hey, I don't like that I'm not getting back all my energy, okay, but you're giving me all this chaos, all this entropy, okay, I'll go ahead and do that deal, okay. But you can't expect somebody to invest $1,000, okay, and only get $10 back and get the entropy. And Gibbs going to say, heck no, okay. If you make this enthalpy value too positive, if it makes it too positive, okay, the entropy is not going to be enough. The Lamborghini ride's just not going to be enough for the amount of money that you're going to spend, if all of this makes sense. So I'm trying to use an analogy that might make sense to you. Okay, so let's talk about something that doesn't take place because the enthalpy value is just too large. Okay, and that would be something like iodine in water. Okay, so let's say we're going to start at the same place, kind of like right here. Okay, and the first thing is we have to separate the solute particles. Okay, well, iodine. Okay, if you don't know anything about iodine is nonpolar. Okay, it has no positive or negative side to it. So there's not a whole lot of attraction. In fact, the only thing that's creating any type of interaction is that you can distort the electron cloud and it creates some induced dipole moments, and those are called London dispersion forces. And that's the lowest type of intermolecular force that we can have. So the delta H1, okay, is going to be fairly small as far as separating, the iodine in the water, okay? So that's going to be, we'll just use 2 plus signs here, okay? Because just dispersion forces to separate the iodine, okay? Now to separate the solvent particles, okay, remember that's going to be hydrogen bonding, okay? That one's pretty high. We're going to say hydrogen bonding, we use like 3 plus signs. So it would make that one a little bit larger. So delta H2 is going to be positive, 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 right? Okay, and this is LDs, okay, and this is going to be hydrogen bonding. And to get the return, it's going to be iodine interacting with water. Well, if iodine doesn't have a partial positive or negative side, like the water molecule has, there's not a whole lot of interaction, okay? In fact, the LDs in a water molecule is pretty low because the molar mass is only 18 grams per mole. So my return here of delta H3 is going to be small because the LDs are going to be small. And what you find out is you got this massive delta H here. This delta H is going to be super positive in order to get iodine to dissolve in water. Okay, now if we take a look at Gibbs free energy for this situation of delta H minus T delta S, if we have a very large enthalpy change, well, that makes this number super positive, right? And if the entropy change is smaller than the enthalpy change, that would be like doing this, 100 minus 50, okay? Well, that would give you a positive 50. This is not going to take place, okay? That's why if you take something like iodine and stick it into water, it, Gibbs wants the entropy, but it's not willing to pay all of this money for a little return in money to get the entropy to say it's not worth it, okay? You're going to have a delta G that's positive, and the chemical reaction will not take place. So we have this saying in chemistry, and it's like dissolves like, okay? If we have something that's ionic, which is the extreme case of polar, so I'm going to call it ionic / polar, it will only dissolve in polar substances. Like dissolves like, okay? Over here, I have something that is nonpolar in something that's polar. That will not take place, okay? In fact, if I want the iodine to dissolve in something, it can't be polar. Like dissolves like means I have to have the same thing dissolving the same thing. So if I want iodine to dissolve in something, I have to put it into something that is nonpolar, kind of like iodine in hexane. Okay, let's take a look at the enthalpy diagram. I had to make it a little bit smaller, but I think you guys will get the point. Okay, so here we go. We're going to start out. To separate the iodine, it's going to be small. It's just going to be LDs, London dispersion forces. So delta H1 is going to be LDs. Okay, delta H2, this is nonpolar. So let me label each of these as nonpolar. And that's going to be LD. So delta H2 is going to be LDs. Okay, and then the interaction that occurs between iodine and hexane is going to be LDs. So delta H3 is going to be LDs as well. So you invested a little, you got a little bit back, but what you're going to find out here is that this delta H here is small. And remember, if delta H is small, Gibbs free energy will say, hey, I'm willing to pay $10 or $20 to get all this entropy, and that will take place. Remember, delta G is equal to delta H minus T delta S. As long as this enthalpy change is a small positive number, and you subtract a larger positive number, okay, like I said, 50 minus 100, you will get a negative number. And you'll say, hey, yeah, I'll do that deal, okay? And the reaction will take place because the delta G is negative, okay? So in summary, okay, for this whole process, we have this saying that's called like dissolves like. So if you have something that's nonpolar, it'll dissolve in something that's nonpolar. If you have something that's ionic, which is the extreme case of polar, if you have something that's ionic or polar, it will dissolve in polar. Okay? But if you have something that's nonpolar, it will not dissolve in something that's polar. And if you have a solute that's polar, it will not dissolve in something that's nonpolar. Like dissolves like. If you found this information helpful, please give it a like and subscribe. And when you add that comment, it really pushes this content to other students that might be interested in learning chemistry.